Okay, so last time I rocked everyone's world by saying that that is what carbon dioxide is, right? And you guys quickly pointed out that I was wrong. But I said I'm a professor, which means what?
You're always right.
I can't be wrong. I never make mistakes, okay? If you find a typo on an exam, you know you just don't know how to spell something, okay? That's how it works, right? But actually, I'm not wrong in this case. And remember, these are one of the issues. Remember I said you guys were going to fight me a lot, right? This is one of the places where you guys are going to fight me. Because I'm going to give you a question, and your immediate response is, there is an answer to this, okay? Now, I'm not faulting you guys for this. This is just kind of how most classes go, right? You know, in math class, there is an answer and plenty of wrong answers, yes? So it kind of depends on what the question being asked is. But I'm saying that this is a valid Lewis structure of carbon dioxide. Have we violated any rules to get to this answer?
No.
No, right? So far we've followed every rule, right? Now what you guys wanted to do, and what you guys were hoping would happen, right, is if you allow me just to erase these arrows here, right, with the arrow pushing, the electron pushing arrows. And let's do, yeah, that's fine, we can do this, right? What you guys wanted me to do was something like this instead, right? Where, let's see, black in the middle, those are green, here, 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 okay. Right? Oof, that looks kind of, whatever, it's fine, you guys get the point. It's not the perfect drawing. That's what most of you guys probably have, right? And that's what you guys want, right? Why? Why do we want that?
One of the first things that is taught about Lewis structures is that the best, quote unquote, best overall structure is one where it gets as close to neutrality as possible.
Neutrality in what way?
So like, because oxygen has 6 valence electrons, it really only needs 2 in its outermost shell in order to satisfy the octet rule, which would mean with the 6 electrons by itself, it would have a -2 charge, but when it has 2 bonds to it, it would have a neutral oxidation state.
Okay, what's Daniel talking about? Yeah.
Formal charges.
Formal charges. Got it? So I'm not saying what Daniel said is incorrect, right? But the stuff that we're mentioning here, the thing that I'm trying to get you guys to point at is a formal charge. Guess what formal charges are? They're a charge, and they are a formality. Got it? You guys understand what I mean with this? They are for us. Now, what do I mean by this? They're a way for us to track where electrons are. They're a way for us to say, hey, there's something unusual going on over here. I better pay attention to it. Do you guys catch what I mean by this? Right, electrons are just electrons. They're just hopping around all over the place, okay? Formal charges are a way for us to say, oh look, there's something weird going on with the electrons over here. I better go pay attention to this. I think at this point you guys already have the mantra down, right? What does chemistry and how does organic chemistry work? Something negative and positive, yada, 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 right? So, following along with this, if I find a negative formal charge, right, that's usually a good place for you guys to start your reaction, okay? So formal charges are going to be one of the key tools that you guys have of assessing what reactivity is going on, okay? In fact, in a little bit, we're going to introduce the idea of nucleophiles and electrophiles. And all that is something negative attacking something positive, okay? But we look for these negatives and positives, and formal charges are a good place to start with this, okay? Does everyone kind of make sense on this, right? We kind of remember a little bit about formal charges. You guys all remember how to calculate them? Everybody does. Good. So I don't have to talk about everyone 100%, never going to miss it on the exam, right?
No, please don't.
Thank you. I appreciate it. I like that somebody's brave enough to speak up about that, right? And I want everyone to kind of get comfortable with that in here, okay? I've been teaching for a while, okay? I'm pretty good at explaining things. I'm not claiming to be the best. I'm the best one in this room by the name of Patrick, right? There's no one else Patrick, right? Okay, I'm the best explainer named Patrick in this room, okay?
Someone might have a middle name, Patrick.
That could be the case, right? Right, but the point being, I can't help you guys out if you don't let me know, right? I can't read your guys' mind, right? Like, hey, Dr. H, I don't remember, could you show me, right? I promise no one's gonna laugh at you, right? We're all in here together to learn about things. Sound good? Okay, so let's take a peek at this. Oh, let me add one thing here. So to carry on with what Daniel was talking about there, one of the most important checks is formal charge, okay? All right. So let me show you guys how I do formal charge. For those of you guys who are in my Gen Chem class, this is not anything different from what I did there. All right, so the way I do formal charge, or the way I should say I teach formal charge, is using the science circle. You guys remember the science circle?
Yes.
Some of you guys do, some of you guys don't.
The
Some of you guys might have learned a formula to do it. Okay, I don't care what way you do it, what do I care about? That it's right. Got it? So here's how science circle works. My science circle surrounds the atom that I am looking at, okay? And it cuts every bond around that atom in half. You guys with me? Okay, so we put an imaginary circle around the atom we're looking at, and we cut all the bonds in half there. What I do next, I guess we can use purple here, is I count the electrons in the circle, okay? So 1, 2, 3, 4, 5, 6, 7, okay? If I'm imaginarily, is that a word? It sounds about a word, right? If I'm imagining that I'm cutting a bond in half, okay, I assume that one electron from that bond is inside the circle. You guys with me? That's just kind of the convention that we're doing with the science circle. Got it? We cut this bond in half, so one electron per half of a bond inside the circle. Good? So we got 7 in there, okay? 7 electrons in the circle. How many valence electrons does oxygen start out with? 6, okay? You guys remember last time we talked about where we get that 6 from, right? That's from the periodic table, talked about electron configurations, yada, 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 all that kind of stuff, right? What's 6 minus 7?
-1.
-1. What's the formal charge on oxygen?
-1.
You guys with me? That's all it is, okay? Good? Science circle, valence electrons minus what's in the circle, -1 formal charge. Should you guys explicitly put any non-zero formal charges into your Lewis structures? Yes. Any formal charge that is not 0 needs to be explicitly shown. Why? Electrons do chemistry, negative goes to positive, blah, 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 blah. Got it? You guys with me on this?
Mm-hmm.
Okay, so do the rest of the formal charges for the other 5 remaining. Right, so we got 1, 2, 3, 4, 5. Give me the formal charges. Looks like we're kind of wrapping up here. So looking at this carbon right here up in the top middle, what do we have? 0, okay. Oxygen over here on the right? +1. Everybody good on that?
Mm-hmm.
Okay. Going down to the bottom, left to right, what do we have? Oxygen on the left? 0. Carbon?
0.
All right, and other oxygen?
0.
Cool, got it? Which one's the correct structure? Both. Which one is the predominant structure?
The second
One on the bottom, got it? You guys with me on this? I'm not trying to deceive you guys. I'm not trying to make you feel dumb. I'm saying both of these are correct Lewis structures. One of them is far more correct than the other. You guys with me on this? This is important. Okay? Yeah, what's up?
Is the bottom one predominant because it has a formal charge of 0?
Right, so that's the next question. Why is the one on the bottom more correct? So we have some rules for formal charges and Lewis structures. The most important rule is to minimize the formal charges that you have. If you want to have one statement for you to tattoo on the inside of your elbow, okay, tattoo, minimize formal charges, okay? And on the other elbow tattoo, don't waste money, all right? So, you guys with me on this?
Mm-hmm.
So I shouldn't get a tattoo that says OChem for life.
No, that, you should get a whole sleeve of that, right? Multiple times.
Just fill it with benzene rings.
There it is. I think that's somewhere in scripture, right? You guys with me on this? So minimize formal charges. That comes in 2 flavors. What I mean by this is, if you can get everything to 0, that's usually the way to go. Got it? You have a question?
Yeah, just
Yeah.
relating to the convention for indicating a non-zero formal charge.
Yeah.
Is that exactly how you did it?
Yeah. So typically formal charges are done like in a circle is kind of what it is. Is that what you mean? Or
How, like, if you were writing it out and you want to
Yeah.
indicate this, like on a text or something.
yeah, just like that is fine. Yep. Yeah. The zeros you don't have to put, right? I just put that there for our sake here.
Would like the circle is part of
This?
it? Yeah.
Yeah. Mm-hmm. Yeah. Yes.
But, so do you also want us to do that thing where you put the Lewis structure in parentheses?
No, we don't have to do that. Yeah. Yeah.
Is that just for ions, or do we get the ions from the formal charge?
Good question. So hang on to that thought, right? You guys, where was I? Oh, right. Talking about the minimizing the formal charges. So the closer we can get the atoms to 0 is what the name of the game is. Okay. If we can move bonds around and not violate any rules, okay, the formal charges with mostly zeros are going to be better. Okay. That's what I mean by minimize formal charges. The other end of this is if I can make something less negative or less positive. What I mean is if I have a formal charge, if I have a Lewis structure and I calculate the formal charge and it ends up as a +3, but I can rearrange some electrons to end up as a +1. We'll pick the +1 over the +3. Got it? That's what I mean by minimizing, just getting them close to 0. The individual atom and the overall molecule. Okay? Everybody following along with that? Yeah.
Wouldn't they both have an overall formal charge of 0 because the +1 would cancel the negative?
So that's what Andy was asking there, right? So why do we care about formal charges, or what does it have to mean, or how do we use all this kind of stuff? The sum of the formal charges has to be equal to the molecular charge. What was the molecular charge on CO2?
0.
0. It's a neutral molecule, got it? So -1 plus 0 plus 1 equals 0, right? 0, 0, 0. How do I know when I've done the correct formal charges? Well, your formal charge is going to equal the molecular charge. Got it? So there's a lot that goes into formal charge, okay? There's a lot that goes into this. Your book spent some time on it. There's a lot of detail online, okay? There's plenty of good videos, important videos. This is one of the key tools that you guys are going to forget to do, okay? So don't forget it, right? Yep.
What's the missing octet step again?
So this is, remember when we go through and we fill in the octets, we ended up with carbon only having 2 bonds, and so we have to come back and make double and triple bonds. That's usually what happens there, right? Making multiple bonds. Good. Yeah.
How many bonds can carbon make?
Ah, that is the question, right? So the answer is up to 4, except for when it has to go beyond that. Wasn't that helpful?
So-
Now, let me answer your question in a better way, right? To get a little bit into the mindset of what we need to start asking, at least for organic chemistry. How many bonds does carbon typically make? 4. Got it? So that can be any combination of 1 sigma bond, right? 2 sigma bond and 2 pi, a single, a triple, 2 double, 4 single, right? There's many different combinations of how we can get to that number 4. And that's kind of what we're gonna see for the rest of the semester, okay? Will we ever see a carbon with less than 3 bonds?
Probably.
A lot, actually. Okay, that's gonna be the next bane of your existence. Something called a carbocation, okay?
I'm
Can-
sorry, a what?
We'll talk about it when we get there, okay? We're gonna see carbon occasionally make more than 4 bonds. These very, very rare cases called superacids, okay? We'll talk a little bit about those when we get to the second semester, all right? But predominantly, carbon's gonna hang around with 4 bonds. Cool.
According to my juice, an acid is any hydrogen-containing
Calling you out.
Why the hell do I need a lecture? All right, yeah, you guys just listen.
So, Dr. Hillsham, you don't know what you're talking about.
Thank you, folks. All right. Good thing they're never listening to us unless we want them to. All right. So anyway, okay. So what is the relationship between our 2 molecules here then? Let me just take these and draw them on a separate page here so we can clean things up just a bit. So we have carbon, oxygen, oxygen, right? Carbon, oxygen, oxygen. I promise I'm drawing them for a reason here. Let me just, let's see, we had, yeah, we can do this. Do this. Okay, so start looking at the top 2 up here. What's the relationship between those 2? Do I change the connectivity of my atoms, aka, do I change the carbon being bound to 2 oxygens? No, right? So the atoms are in the same place. What's the only thing that's moving?
The electron.
The electrons, okay? That's going to be mostly true for everything that we do, okay? Occasionally we're going to be moving atoms a lot in the sense of making or breaking bonds. But what I mean is, if we're just looking at the relationship between 2 distinct molecules, okay? If the atoms rearrange, we have a different situation. We'll talk about that in just a minute, okay? But if you're looking at these 2 and just saying, only the electrons are moving, okay? The relationship between these 2 are resonance structures, okay? Resonance structures.
Really?
Mm-hmm.
I thought resonance structures is when like, oh,
It is.
So, I have a question for you. Can you guys show me the arrows, the electron pushing arrows, the electron moving arrows to get from here to here? Show me the arrows of how the electrons move to get from here to here. Remember, with arrows, they start where the electrons begin to where they end up. So from where they begin to where they end up. So see if you guys can come up with the arrows.
From which to which, okay?
From here to here. How can we get from here to here?
Wait, I'm sorry, I missed that. From where to where?
How do we get from here to here? With our electron pushing arrows. All right, let's see what we can do here. I need to go from here to here. So between this carbon and oxygen, I need to make another bond, right? What makes a bond? Electrons. Okay, where am I going to grab electrons from? Well, the lone pairs. Got it? So this is one thing to pay attention to. Lone pairs can turn into bonds, right? So I'm gonna take this lone pair, or the one on the bottom, it doesn't matter, right? And turn it into a bond between the carbon and the oxygen. Everybody with me on what that arrow is representing, okay? Now what else has to happen? Between this carbon and oxygen, what do I have to do?
Break a bond.
Break a bond, got it? So I'm starting at the bond, it doesn't matter, the orange or the black one, and I'm turning it into a lone pair on the oxygen. Good? Everybody following along with this? So just to add some color, let's say that that's the bond that we made, right? And we just say that that's the lone pair that we turned the bond from, right? Everybody with me? So you make a bond, you typically break a bond afterwards. That's kind of how it goes. Make a bond, break a bond. Yeah.
So if that were to happen, would it be true to say that it took more energy to break the bond than it would be to?
Good question. The answer is maybe. Right?
Maybe.
Yeah. So we'll get into that a little bit later too. Okay. Everybody with me on this? Everybody see how the colors kind of match up and where the electrons are flowing to? Okay. So when you're doing resonance structures, we're not moving atoms, we're moving electrons. What are we moving? Lone pairs and pi bonds. Those are the only things that move when we're doing resonance structures. Okay. Lone pairs, pi bonds. Not sigma bonds. If I break sigma bonds, I'm changing the connectivity. Okay? Everybody with me on this? This is another one of these things that you have to learn how to do. Okay? Resonance structures is key, important, vital detail. Have to get comfortable doing them. On the first exam, I'm going to be asking us to draw resonance structures. Okay? I'm going to ask you to show me the arrows, showing the movement of electrons for these things. Okay? Okay? Now, oh yeah, what's up?
Sorry, can you just repeat, you said sigma bonds are not moving because of,
They're not moving when we're drawing resonance structures. Because then we'd be breaking atoms apart, right? A sigma bond is a single bond. If I break those, then we no longer have the same molecule, right? Okay? Now, part of the definition of resonance structures is we have to get back to where we started from. So I think you guys know what's going to happen. We went from here to here, and I'll go from here back up to there, right? So draw the arrows to go backwards.
You have to draw that line as part of arrow pushing.
I'm showing you guys that, yeah. We could do it as a, yeah, I should probably not to confuse you guys. Let me draw that in red. I'll tell you guys what it is here. It's me being lazy at the beginning. Let's do, pink sounds good. Okay, so to go from here back up to here, I have to make a double bond between here, and I have to break one of the pi bonds there. So what I'm going to do is this, right? And that right there. Everybody following that flow? Pretty easy, right? Yeah.
So does this mean there are 3 resonance structures technically? So because, okay.
Okay. Everybody with me on the arrow pushing here real quick. So there's 2 ways that we represent resonance structures. So that's kind of what I'm trying to show you guys here in the red. Typically, if you see me draw a red, or like an arrow that has 2 ends on it, I'm saying those are resonance structures between the 2, okay? In the book, sometimes you see it look like the equilibrium arrows, that it kind of looks like that, right? Either way is fine. But that's all I'm showing you guys with that, right? Yep.
Can you draw the arrows above or below? Or does it not matter?
I'm sorry, what?
Can you draw the arrows above and below? Or does it matter?
No, it doesn't matter, yeah. So that, there's no particular reason why I drew it here, otherwise it would just
Okay.
bump into that, right? Yeah.
When we're showing the movement of electrons, do we have to do the forward and the backward?
Yeah, right, that's part of the definition of resonance structures, right? If these are related, you should be able to go back and forth between the 2.
Okay.
Yeah? Okay? Yeah.
In addition to like drawing arrows this way, could you also draw the arrows like oxygen to oxygen and then bond from one side of the carbon to the other side of the carbon?
I'm not quite following what you're asking.
Instead of like breaking the bond
Yeah,
and putting the electrons from the bond into the oxygen, could you just put the bond on the other side of the carbon? If you're trying to go.
no, yeah,
So you have to break the bond.
yeah, yeah. You're talking about like doing something like this maybe?
Yeah.
Yeah, no, that's not the correct flow with electrons there. Okay, yeah. Okay, so I drew this down here for a reason. There's another resonance structure. Find that resonance structure and show me the arrows for how these are all related, okay?
Do you want one for each?
Hmm?
Do you want one for each of the resonance structures?
Sure, sounds good. What's up? Mm-hmm. Well, no, I didn't fill them all in here. I'm just saying there's one more resonance structure. I just left that stuff out. No. I didn't complete it for you. I'm saying, yeah, you guys need to go through and do it all. Say what it is and then how to work it. That's all the arrows do, right? Sorry, I didn't mean to confuse you like this, right? Yeah. No, they didn't all magically disappear. Throw an arrow flying off to infinity, right?
Because everything is still.
All the other ones, right? All of them.
This carbon is not.
Yeah.
So there's almost no way that the oxygen can sit on the carbon. It's just too
No, right, because you're not completely. Yeah. All right, so it looks like we're kind of getting there. So the missing resonance structure is going to look something like this, right? Guys with me on this? Remember, this is basically, I think this is the drawing that we had on the previous slide, right? What's the relationship between these two? Are they identical?
They're mirror images of each other.
If I walk up to a mirror, isn't that identical what I'm seeing?
It's reverse, it's reflection.
Right, but it's me that I'm seeing, right? It's the same thing, right? So this is something to start to think about, what we'll get into here, okay? The relationship between molecules, all right? How can we draw arrows to get from here to here, right? That's a question. How can we get arrows to go from here to here? Right? Be some good practice for you guys to go through and do that, okay? See what you guys can come up with. If you guys are struggling with it, come see me then, okay? Everybody feeling all right though about formal charges here? Starting to get a little bit of the hang of resonance structures, all that kind of stuff? What's up?
Do we go from, like, how do we know not to go from the second one to the third one? Is it always the
From
first
here to
one?
here?
Yeah.
Yeah, you can do that.
You can, okay.
Yeah.
But not the first one to the third one, or does it matter?
All of them, right? All resonance structures have to be related to each other. Yeah.
But in order to go from the second to the third, wouldn't you have to essentially move two pairs on each side?
Interesting, huh?
So that would take a lot more energy for those to turn into each other.
I'm not talking about the energies of any of these yet. Just saying how they relate with the movement of electrons. Now that's important to think about, right? Okay? Question, what are the consequences of a resonance structure? So let's think about this for a second, okay? Let's go to something maybe a little bit easier. Okay, so I want you guys to draw the Lewis structure and draw the resonance structures for that right there, which is called
Nitrate.
nitrate. Is it important to remember your polyatomics in this class?
Yes.
Absolutely. Okay, so draw your Lewis structure, draw your resonance structures for nitrate. When you're drawing your resonance structures, go through and draw your electron pushing arrows. Okay?
So no lazy shortcuts on this?
What's my rule on shortcuts? You can get a shortcut when you. Anybody get their PhD over the weekend?
Yes.
Okay, no
I wouldn't
shortcuts.
put
then.
it past Murray, honestly.
Excuse me. Thank you.
Okay, you guys can bring that. Basic math. It's all good. It's all good. What are your formal charges?
Oh.
Forget to show your formal charges if they exist, which they will. Which one? That one? Looks okay, except you're missing a formal charge. Good. Everybody get at least one Lewis structure drawn with those formal charges? Some of you guys probably had that blue pi bond in a different place though, right? Does it mean I'm right and you're wrong?
Isn't that the point of resonance structures?
Well, that's the point of resonance structures, got it? Let's draw a resonance structure. So follow along. So what can we move in a resonance structure? Lone pairs can get turned into pi bonds. Can lone pairs be turned into sigma bonds?
No.
No.
No. So lone pairs can be turned into pi bonds, and pi bonds can be turned into lone pairs. Pi bonds can also be turned into other pi bonds. We'll look at that in just a little bit, okay? Everybody with me on these three things that we can do? Lone pairs into pi bonds into lone pairs, or pi bonds into other pi bonds. Good?
Mm-hmm.
Now, these lone pairs and pi bonds have to be next door to each other. Okay, so that's one of these rules. We'll talk about that in just a minute, what we mean with that, okay? I just told you guys 4 important things. What we can transform, and that they have to be next door to each other. Everybody catch that? Lone pairs into pi bonds into lone pairs and, pi bonds into other pi bonds. 3 important things, but they all have to be next door to each other. Okay, yeah.
By next door, do you mean like in the previous example where we were going from 2 to 3, that wouldn't actually work because they're not really next door?
No, they're all connected is what I mean. Right? Here's what I mean. So watch. Good?
Mhm.
What do I have to break now? I made a bond, so now I need to break a bond. Now what's the only bond I can break in a resonance structure?
Pi bond.
Pi bond, got it? Do you see how these are next door, right? Here's where I'm starting, here's your next door neighbor, and this is next door to that. Got what I mean with this? These are all connected to each other. Okay? My pi bond, I'm going to turn into a lone pair. Draw that resonance structure. And then draw the next one. Okay? Oops. Jeez, I'm struggling today with colors. All right. Everybody with me still? What am I missing? Resonance structures are all related.
So the last one needs to connect to the first.
We should be able to go from here back to here, got it? So that's another little, let's say, a little practice for you guys at home, right? Fill that in. How can we close the loop there? Question, what's the consequences of drawing a resonance structure here? Now here's something important to pay attention to, and I'll come back to this over and over and over again, okay? So if you think about what we mentioned with formal charges, right? We said that in general, we want to minimize the formal charges possible. We want to get them closer to 0. Yeah? Okay. Well, are the formal charges as minimal as we can get here? Wait a minute though. I made a mistake. Oh, hang on, pay attention. Okay, right? I think I made a mistake. Because if I do this, right? If I do that, then this has a 0 formal charge and that has a 0 formal charge. Ah, sorry guys, just erase everything you did, yeah? No, why? Too many electrons on the nitrogen there, right? It's got access to 10 electrons. Is nitrogen going to violate the octet rule?
Yes.
No. Okay? So be careful. This is a common mistake. Okay? So don't do that. Okay, so can I do anything else with the formal charges? Can I make them any closer to 0? Yes, by drawing resonance structures. You guys with me? Let me color code something here so we're all paying attention. I'll do it in black. Take a look at this oxygen in black up here. So we have 3 resonance structures, okay? What's the charge that that oxygen is feeling in black? Well, it's got a negative, it's got a 0, and it's got a negative. So what charge is that thing feeling? Two of the times it's negative, and out of the 3 times, right? So really it has more of a charge of about
0.66?
about negative 2/3. You guys with me on this? Is that smaller than negative 1?
Yes.
Yeah. So a couple things to think about, okay? These are what's known as equivalent resonance structures. Now what do we mean by equivalent resonance structures? We don't change the total charge, okay? There's still always 2 minuses and 1 plus, okay? The other way of thinking about it is kind of if you close your eyes, right? Well, let me start a different way here, right? If you kind of look at this, all I'm doing is it looks like I'm just rotating this bond around. You guys see what I mean by this? I'm just kind of picking the molecule up and spinning it, right? So if that's what it looks like when you're drawing resonance structures, you're probably drawing equivalent resonance structures. So if you go back to the previous example we did, you guys are saying, oh, it looks like I flipped it, or it's a mirror, all that kind of stuff. All right, that's what's going on there too, okay? Equivalent, this is one of the key things. I'm getting a lot of key things in only the second week, huh? Right? Equivalent resonance structures are extremely stabilizing to molecules and to charges. The more equivalent resonance structures you can draw, the more stable that molecule is, okay? I'm not saying it's less reactive, I'm saying it's more stable. In some cases, it's actually more reactive. Right? We'll talk about what that means.
So, reactive and stable, by reactive you mean its tendency to have a chemical reaction?
Let's hang on to that thought. We'll talk about reactivity in a little bit, okay?
But for stability, do you just mean something's natural tendency to like be
Lower energy.
Okay.
That's what I mean, yeah. Okay, everybody with me on this? Equivalent resonance structure is good. Being able to draw resonance structure is good. Being able to draw arrows, gooder, right? Guys with me? Lots of important stuff today, okay? So the consequence of this is that we spread the charges out on the oxygens. Now I can read your minds. I lied to you earlier, okay? I can read your minds, okay? Only because it's a common question that like always comes up, right? What do you guys know about oxygen? Pretty darn electronegative. In fact, it's the second most. Now, something that we talked about in Gen Chem, right, it's one of these rules of formal charges. So if you want to go back in your notes and kind of add it into your formal charges, rules, right? I'm talking about here, right? If we have to put a negative charge, we want to put it on the most electronegative atom. If we have to put a positive charge, we put it on the least electronegative atom. Got it? Now, in our minds, sometimes that gets translated to, oxygen's always going to be negative, it's fine, right? Is that the case? Is oxygen okay being negative? Yeah. Does it want to be negative? Right? Being negative, or let me back up here for a second. Having a formal charge is like being in a bad mood. Okay? You guys with me on this? Everybody in here has a varying degree of good or bad mood right now. Right? You have to wake up early. Have to listen to this guy drone on at the front. Okay? He's making me think. Right? All check marks in the bad mood department. Right? Why are you guys smiling and laughing? No, that's not the case, Dr. H.
You're a Disney villain, Dr. H.
All right? You guys with me on this? Everyone can handle certain degrees of bad mood. Same thing with atoms. Some are better at handling that mood than others. You guys with me on this? Okay? Now, if you have to be in a bad mood, what's the best thing to do? Spread it to somebody else. Make their day miserable, right? Okay? I think that's in the Bible somewhere too, right?
Misery loves company.
I forget. No, I'm joking, of course, right? But you guys with me on this? So, it's of course don't do that. Right? But this is the idea of a resonance structure. We're taking a bad mood, that negative charge, and we're spreading it out over multiple atoms. Okay? That's the idea of resonance structures. They stabilize the molecules by spreading that charge out. The more equivalent resonance structures you can draw, aka the more equally, if you want to think about this, right? The more equal this distribution of charges, the better. Okay? What's up?
So I'm sorry, I'm still a little bit confused on the line arrow pushing thing.
Yep.
So when you go from the first one to the second one, I understand you're showing how the second one, how it got there.
Yep.
Do we have to show how it can go back?
Yes.
Did you do that here? Or?
No. I went from here to here, right? So I made this pink bond, and I turned that pink bond into those electrons up there.
Okay, so I hate to ask it like this, but for a test, you want to see
Yeah.
5 or 6 more of it.
Yep, you could show that one, you could show these going back and forth, you could show the first two going back and forth. Yeah, what's up?
Do we get to use colored pens on the test?
Sure, that's right.
So would you want us to draw arrows for the third one?
Mm-hmm. Yep, there's definitely plenty of missing arrows to fill in here. Mm-hmm. Everybody get the important things about resonance. Spread out charge, stabilized molecule, good way to go, right? In fact, remember I told you that formal charges are what? They're a charge, which are a formality, right? They're us to say, hey, there's something unusual going on. Okay? They're for us to pay attention to things. You see a formal charge, say, I better see if I can do anything with that charge. Can I put it on a different atom? Okay? Did I draw something incorrectly? Am I missing a resonance structure? Right? All of these are important questions to ask. They're for us to track where the electrons are. And if we can't do anything else with them, then we take a look for resonance structures to spread them out, to stabilize those charges. Good? I'm going to be talking about resonance a lot. Okay? A lot. Yeah.
Are there usually 3 resonance structures?
There's no answer to that. It depends. Right? And this is one of the tricky things. It's an important question. How do I know how many resonance structures there are? The answer is, until you can't draw any more. Okay? Now, the good news with this is you guys are going to get plenty of practice drawing these. Okay? The bad news is, because you guys get plenty of practice, we get complacent. Okay? What I say about skipping steps, though?
No doing it till we're PhDs?
Right, no skipping steps. Okay? Now, what are the limitations of resonance structures? We can only move what? Lone pairs, pi bonds, and those pi bonds have to be next to each other. Got it? So that's kind of a way to start to narrow down how many resonance structures you guys can reasonably draw. Okay? Good? All right. Okay? Have at it. Go ahead and draw me the correct molecular structure for that molecule. The correct molecular structure. Not necessarily a Lewis structure. Draw me the best representation for physically how that molecule looks.
So with geometric?
Oh yeah. I mean, I've seen better, you know. Right? So 4 electrons coming from the carbon, 4 electrons coming from the 4 hydrogens, yes? Okay, cool. So we would draw a Lewis structure that probably started off something like this. Everyone got happy and confident, right? It's not a bad Lewis drawing, right? Lewis structure. Is that actually how the molecule is, though? No, the implication here is that everything lies in the same plane. Okay? Is this a planar molecule? No. Okay? In fact, this is what would be actually known as a tetrahedral molecule, right? Oops. H-E-D-R-A-L, tetrahedral. Okay? So if I asked you to draw the correct molecule, the molecular structure, on an exam, right, that is not correct. Okay? That's not a correct representation of what it is on the molecular level, right? So we have to be able to draw a tetrahedron. Well, first of all, what's a tetrahedron? A tetrahedron is a 4-sided 3-dimensional shape, right? So it's kind of like that, it kind of almost looks like a pyramid, right? So if we have 4 points, right? And we connect all those points in space. You guys with me on this? Right? The reason why it's called tetra, right, is because it has 4 faces to it, right? Doesn't mean that there's 4 atoms involved. Just means that there's 4 faces to the 3-dimensional shape. Right? Just like we'll learn about something called octahedral, doesn't mean 8 atoms, it just means 8 faces. Okay? You guys with me on this? So we have to represent something in 3 dimensions on a 2-dimensional piece of paper. Can we do that? Can we do it easily? Yes. Right? How do I know you guys can do it easily? Because if I asked you guys to draw a cube for me, could you guys draw a cube? Sure, right? We just have to, draw a little square. Right? We put some lines going back that kind of represent depth, right? And we could even, if we want to go for the bonus points, right, we could draw some dotted in the back here, right? Just to show off our skills. Okay. Is that really a 3-dimensional thing that I drew? No, but you guys are looking at it and we interpret it in such a way because we give it dimensions, right? We are trying to draw a 3-dimensional shape on a 2-dimensional plane. We lose information as we change dimensions, right? You guys with me on this? So we have to have some conventions to kind of go between, right? Say, okay, I know we're losing dimensional space here, but we have to understand that it's there. All right, so how do we draw a tetrahedron? Every tetrahedron is going to look the same way, for the most part, okay? There's my carbon, okay? I'm going to put 4 things around it. Those 4 things are going to look like this. The lines that you guys are used to drawing, okay? The lines that you guys are used to drawing, like just the plain straight lines, represent things that are in the plane of the paper or whatever it is that you're drawing on. You with me on that? A wedge bond means it's coming out of the plane. So we have something sticking out of the board here. Okay? A dash is going into the board. Good? That's all there is. So if you just can draw that basic tetrahedron shape, you can fill in whatever you want to around it. You guys with me? Okay, that's all it is. Until it's not. Okay? But the best way to represent a tetrahedron is you have 2 things in the plane of the paper, one coming in and one going out. All right? Everybody with me on this? Why did I draw it this way? Yeah, what's up?
The question, does it have to be in that order specifically? Like
Yeah, so hang on to that thought real quick. Yep. So why did I draw it this way? Now, here's the other question, right? Why did I draw it with specifically that angle there? So what is the idealized angle in any tetrahedral molecule? Yeah?
109.5?
109.5, got it? So when we are drawing things, and we're going to be drawing things a lot, we want to make sure that we draw them as close as to what the actual representation of that molecule is. Okay? As close as reasonably possible. So we're going to learn a new way to draw things in organic chemistry. But if we have a 109 degree bond angle, we try and represent it as best as we can. If we have a 90-degree bond angle, we try and represent it as best as we can, et cetera, et cetera, et cetera. You guys with me on this? So when we're drawing molecular structure, which is what I expect you guys to be able to draw, we try and draw them in a way where it's as close as reasonably possible to their actual shape. Because shape is what's important, okay? Shape determines function, shape determines reactivity. Good? So, in a tetrahedral molecule, okay, so 109.5 degrees is the idealized bond angle, okay? We typically have a central atom with 4 things around it, okay? Does it matter if those 4 things are hydrogen? Not really, right? Could it be 3 hydrogens and something else? Sure, right? What's the hybridization of a tetrahedral molecule?
SP3.
Okay, now what in the world does that mean? Well, first of all, what does it mean to be tetrahedral? Well, Dr. H already answered that question. It means to be, we have a central molecule, 4 things around it, 109.5 degree bond angles. Question, where do electrons live?
In orbitals?
Orbitals. What orbitals do we have available to us here? We have s orbitals and we have p orbitals. Okay, an s orbital is a sphere. What angles exist in a sphere?
360.
Infinite. Got it? They're the most symmetric thing that we can make. What are the angles in a p or for the 3 p orbitals? 90 degrees. Okay. Are the angles here 90? Well, how in the world did we get to 109.5? Is it just because we really wanted to do that? Why do they not make 90-degree angles? Ooh, right? Wouldn't that make more sense? Well, the orbital's already at 90 degrees. So why don't we just do that, right? Do you know why? It's so that I can ask you questions and make you miss things on exams, okay? That's why. Sound good?
Mm-hmm.
You gotta just resign yourself to
Yeah.
Oh yeah, sounds good, whatever, Dr. H, you can't fail us all, man. Right, so that's the question. Why do non-90 degree bond angles exist to begin with? If you go back to the previous example where we did with nitrate there, okay? These have 120 degree bond angles. How in the world do we get 120 from any of this stuff? That's the question to ask, and that's where hybridization comes in, okay? So we'll pick that up next time, and we'll continue on learning how to draw things, okay?